welcome. Eamonn Darcy is my name. I'm the founder and operator of QEQA, the Quantum Education Centre of West Australia. And here we come to the final lesson in the series, the 10 by 10 series, 10 episodes, 10 minutes long or very near about after editing, etc. It's been a journey, and I hope that you've gained a lot of knowledge on quantum computing through this series, and that it will encourage you to study and research further into this amazing technology, because it is amazing. Let's look at what we've learned together. Lesson 1, superposition, probably the most important state of a quantum particle that beggars belief. We still don't understand it, but a quantum particle is in a state of wave-particle duality. So at the same time, it has particle properties and it also has probability wave properties. And it's in a very mysterious state of being, of existence. And this has been proven, so we can't really question it. And with Bell's inequality, it proved that superposition and quantum entanglement existed. And we're getting on to the next one now. Lesson 2 was quantum entanglement, which is absolutely amazing, that you can have two entangled quantum particles that then, no matter how far apart, that entangled particles exist. And they can be hundreds of thousands of kilometers away. And don't forget, these are absolutely minute. There's 9 billion of them in a speck of dust. And yet they can, if you nudge this one to the left, the one 900,000 kilometers away will move a little bit to the left. Somehow they act as if they are one. Now, that's something you just don't find in the classical or Newtonian world we live in. Then we spoke about the interpretations, like the Copenhagen, which is the collapse of the wave function. There's a belief that when you observe, measure, or look at a superposition, a particle that is in superposition, it will collapse to a definite particle with a definite state, which it didn't have until you actually measured it, as weird as that sounds. And then you've got the many worlds, which sort of says, measuring a quantum particle, you become entangled with that particle and you become one. And when you, the wave function never actually collapses anywhere. It's just collapsing in your own world. And that's why it's called the many worlds theorem, because other worlds exist where there's a different outcome, a different measurement outcome. Then when we talk about linear algebra, we just went over the basic and the purpose of it. And then we multiply matrices together, which is something you really, have to be able to do. Then lesson 5 was the Bloch sphere, and that's the visual representation of a qubit, which is a particle in this strange state of superposition, which we can manipulate to do amazing things. And then not only that, we can actually entangle it with another qubit, which means that when you apply a gate to one particle, it immediately is entangled with another qubit. So when they're entangled, by changing one, you automatically change and collapse the other. So that makes it very, very powerful. Then we went on to quantum games in video lesson 7, and we spoke about the Paris-Merman, which is a game that you obviously can't win every time. Logically, in our Newtonian world, in our classical world, you can't win this game all the time. The chances of you winning this game 24 times in a row is 1 in 1,000. Yet a quantum computer will win it every time for an infinite number of games. Now that is just something, again, that defies all logic. And that goes back to the Koch-Specker theorem of quantum contextuality. Then we spoke about quantum teleportation, and people were excited to find out that we've already teleported a quantum particle from Earth to an orbiting spaceship called Messius, and quantum cryptography, which is possibly going to be one of the real first implementations of quantum computing that has a change on society as a whole. Because for the first time, it does give us an unhackable code, because it's based on the collapse of the wave function and the outcome of that collapse, which is the only thing in this universe that we know of that is totally random. Einstein didn't like that. He said God doesn't throw dice. And then today we're going to talk about the different types of quantum computing, because really all that matters with a quantum computer is that we isolate the superposition. Because as soon as we collapse it, it acts just like a normal classical computer. And we're at the stage at the moment of working out and evaluating which subatomic particle gives us the best outcome in both duration and reliability. So there are many ways we can isolate an electron or a photon or an ion. And today I'm going to talk about the different types of quantum computer, or the main types of quantum computer, and who the leading proponents of these are. So let me start my timer, and we will have 10 minutes starting now. Okay, look, let's take the four main types of quantum computer, and that is superconducting, trapped ion, photonics, and NV center. And I'll give a quick overview of the major players and the technology of those four. Okay, the definitive image of a quantum computer is the one you see on your screen now. And this is a superconducting quantum computer. And all of the fancy looking machinery is merely a dilution refrigerator in order to cool the quantum particle down until it stops vibrating, basically, which is as near to absolute zero as we can get, because we can't let it collapse. All of these technologies I'm going to show you are basically, all they're trying to do is isolate the quantum particle to keep the qubit, to keep it in superposition. That's the main thing. Now, the superconducting quantum computer is used mostly by IBM and Google. It was a superconducting quantum computer back in 2019 that very famously achieved quantum supremacy, and it was only a 53 qubit Sycamore processor. I might add that because of decoherence or noise, you've got about 52 of those qubits looking after one of them that's doing the processing. So it's really interesting, but it did actually make a calculation faster than the fastest computer on Earth. Even though the calculation was meaningless, it certainly showed the power of quantum computing. Now look, here's IBM's development roadmap. It's so important. IBM have achieved everything they've said they're going to achieve to date and more. And you can just see, if you look down the bottom, if you go through the evolution of the Falcon to the Hummingbird, Eagle, Osprey, Condor, and beyond, you can see that by 2024, we'll have a quantum processor in the millions of qubits. And that is very, very exciting. Okay, now trapped ion is another competing technology, and it is actually one of the first implementations of a quantum computer. A trapped ion is merely where you shoot a laser at the outer orbital of an atom, and it basically knocks one of the electrons out, leaving one electron. And all an ion is an atom with a charge. And one can then manipulate that electron into different spins and hence quantum states. Another great thing about the trapped ion is that it can work very close to room temperature. It still needs certain refrigeration, but nothing like the refrigeration required for superconducting qubits. Please visit the IonQ website to learn more about the ARIA processor, which IonQ are making very, very big statements about its potential. Now let's have a look at photonics. Now, photonics is based on a photon, which is the empirical unit of light. It has some great advantages in as much as we've already got a network, a fiber optic network based on light. It also operates at room temperature, 4 minutes 24 left. Now, in December 2020, the University of Science and Technology, China, completed a computation, wait for this, 10 trillion times faster than the fastest classical digital computer at the time. That is mind-boggling speed. Now, I'd like to mention that it was a what's called a Gaussian boson sampling, which is based on light anyway. So it was a very biased experiment. But after having said that, the calculation was so unbelievably quick that a lot of people are thinking that the photonic quantum computer is the way of the future. And then let's just finish off with quantum brilliance's what's called envy-centered technology. So the envy center is a naturally occurring vacancy in diamond. And of course, remember the ideal that what we want to do is isolate the quantum particle, isolate the qubit. Well, the natural lattice structure of diamond provides this. So where there is a vacancy, what we do is insert a nitrogen atom, and the nitrogen reacts in a way that the electrons are trapped, and we can use their spin to produce quantum effects and then to produce gates, quantum gates. And of course, then you've got a fully fledged quantum computer, basically. Now, the beauty of envy or diamond technology is that it's at room temperature, but it's also got a long coherence time, even reaching to seconds. And also it's got a very small form factor, which means there will be a handheld device doing this at some stage, which of course will probably never happen in the superconducting world, where the quantum particle has to be cooled down to near absolute freezing. Quantum Brilliance is an Australian company and has a venture with a German quantum startup, and they have already released a suitcase-sized quantum computer, which is in use at the University of West Australia and being tested by the quantum PhD graduates there. And it really is very, very exciting. So you can see that there are different technologies, and the jury really is out on which technology is going to produce the fastest, the longest coherence time, and more reliable communication between qubits. So there's a lot of factors that have to be taken into account. Oh, there's the timer. There's a lot of factors that have to be taken into account. The important thing to realize is that there are different quantum technologies that can produce quantum computing. Thank you very much indeed, and I hope you've enjoyed the 10-part series. I will be doing follow-up presentations episode by episode, so please register your interest, sign up to the Kwekwa YouTube channel, and I look forward to talking to you again in the future. Thank you.